So we are live on YouTube. Welcome everyone to the event jointly organized by the Santa Clara Valley sections of IEEE Women in Engineering and IEEE Computer Society. Today's topic is Unleashing the Power of Generative AI at the Edge. The speakers are Meghana Rao, who is a senior AI developer and evangelist at Intel Corporation, and we also have Vaghesh Patel, who is a staff software engineer, also with Intel Corporation. So Meghana and Vaghesh, over to you. Please introduce yourself and then take control.
Thank you, Vishnu. Hello, everybody, and thank you for the opportunity, IEEE Women in Engineering and Computer Society, for this opportunity for Vaghesh and I to talk about generative AI at the edge. I am a senior developer evangelist at Intel Corporation. I have been at Intel for about 13 years now in the role of a developer advocate for multiple technologies and Intel products over the years. But I have been working in the space of AI for approximately about 8 to 9 years now. And as part of the team at Intel, I am currently responsible for evangelizing IoT and AI products at the edge and in the cloud native ecosystems. So that's my brief introduction. Vaghesh, if you could introduce yourself also, that'd be good.
Yeah, thank you, Meghna. So I'm Vaghesh Patel. I'm software engineer and technical lead at Intel. At Intel, I wore multiple hats as an IoT engineer, as a cloud software developer, DevOps lead, and now I'm working on as a AI solution developer, mostly solving the challenges of infrastructure scalability, MLOps side of it, and then what are the possibilities of solving real life challenges with AI solutions.
Thank you,
Meghna,
Vaghesh. Thank you. So here is the agenda that we would like to cover today. We have all, in some form or the other, been familiarized with traditional AI. So we will talk about how traditional AI is different from generative AI. We will talk about some of the industry applications and common generative AI models that we see in the industry and in the ecosystem today. We'll talk about, what the architecture looks like for large language models and image generation models. And at the end, we will discuss briefly about why generative AI at the edge and how to optimize these Gen AI models for the edge. This topic would not be complete unless we talk about some of the ethical considerations as well as limitations and risks. So that is the topic that we will finally conclude this presentation with. So with that brief agenda, let me go ahead and pop up this slide, which talks about AI as we knew it so far. And as you can see here, AI is actually a program that, can sense, reason, act, and adapt. This applies to machines that are able to mimic the cognitive functions that humans associate with human minds, such as learning and problem solving. So within this broad realm of AI, we have machine learning and deep learning. And machine learning is generally categorized as algorithms whose performance improve as more and more data is exposed to it. And this mostly addresses the statistical problem solving algorithms like linear regression, etc. Deep learning, on the other hand, is a subset, again, of machine learning, where we use multi-layered neural networks that learn, again, from vast amounts of data. But this is more similar to how the brain processes in terms of neurons and how the classification of different types of data come to be is addressed in the subset of deep learning. Now, for both applications of machine learning and deep learning, we have, computer vision, we have statistical applications, anomaly detection, time series analysis, sentiment analysis, and the likes of it. In essence, what all of these applications are that they are discriminative in nature. What does that mean? So these models are trained on labeled data. They work based on predefined rules and patterns, and the prediction they make are towards solving a problem that falls within a decision boundary. So now, compared to this, how is generative AI different? Generative AI is, on the other hand, generates a lot of original content. This is how it differs from discriminative methodologies that are addressed in traditional AI, machine learning, and deep learning. One way to distinguish between traditional AI, which is also considered weak AI, with generative AI is in how the former recognizes a pattern, but generative AI creates new data. This content can actually be of different types. You can generate languages, you can generate images, you can synthesize videos, and even code. And this is actually unleashing enormous amounts of creativity. Now it's creative content generation that is in the primary focus. What is needed here is your idea that turns existing data into new forms that now mimic your idea. So let's take a quick look at different types of applications. And as you can see here, irrespective of the type of data that we are looking at generating, that transcends different types of industries. You could have applications in the retail, healthcare sector, transportation, you name it. You could now use any of these examples that we have articulated here on each column. You could create a chatbot with a question and answering session that could actually be hosted on websites for retail applications. Or you could have, a customer care kind of a scenario. You may want to have articles generated. So you could use the NLP capabilities for summarizing some of the existing data. You could use marketing image generation that could be used for product launches. If you are in the enterprise and you have internal code repositories, you could use code generation using GenAI. You could also use explanation of the code, any kind of test case generation, things like that. And across the board, it doesn't end there, right? You could do text to speech, speech to text, video, you can do video editing, video synthesis. Quite a lot of these applications now are possible through these generative AI models across different industries. And one thing to note here is also that some of these applications could also be multimodal, right? That means that it could have different types of input coming into the model, and then it is generating the output of the type that you desire. Now, let's take a quick look at some of these large language models that exist in the ecosystem today. So if you focus on this particular chart, there are different types of models that you see here. Not just the number of LLM models. As you can see, generative AI in some form has existed before 2020. But since 2020, there has been an exponential growth in the number of LLMs that have come into being. Another thing that we notice through this chart is also the size of the parameters. As you go up the chart, the number of billions of parameters that are used to train these models also significantly increases. And also another aspect here is that some of these models also allow open access. So now organically, this raises a question: is a larger model better? Larger models generally are trained on larger amounts of data, and therefore they have a lot more context to them. You also probably will see fewer hallucinations and mistakes. However, to train these large models with larger number of parameters, you also require an extensive amount of computational resources. Some aspects that we call all of your attention to think about here is the quality of the data that the model is actually trained on could have a significant impact. A smaller model, for example, that is trained on better quality data may actually perform better than a larger model that is trained on poorer quality of data. And this could be, it could become even more pronounced if you're looking at generating content that are very specific. So let us say scientific data. If you're looking at generating scientific questions and answers, then it is really important that the language model also has understanding of such data. So therefore, in addition to the number of parameters of the model, the strength of the model in terms of the number of parameters, together with the quality of the data that the model is trained on, both become equally important. A typical example of this is, for example, Chinchilla, right? It's a 70 billion parameter model, and it was trained on 1.4 trillion tokens. I think the relationship was twice the number of tokens than the number of parameters. That was what was used for Chinchilla. And though it was a smaller model, it performed much better than larger models like Gopher. And on a similar note, for example, Zephyr 7B, which is a much smaller model than Llama 70B, works better for specific use cases. So considering this kind of trade-off before picking the right model for the task at hand becomes important. And later in the session, Vaghesh will walk through generative AI models at the edge and what exactly it entails running large language models at the edge. So since we introduced a couple of terminologies, let me take a brief moment to clarify what it means to have parameters versus tokens. So most of us are probably very familiar with how deep neural networks were trained, right? So essentially, parameters are the numerical value that represents the weight, or it could even be the bias within the neural network. So it's essentially the trained weights that determine how well the model performs. Tokens, on the other hand, are basic units of text that you use to process and generate the language. So let's take an example here. If I say good morning, there are two words in it, and therefore also two tokens. But one general, people tend to, think, are the number of words in the input equal to the number of tokens? It may not be. So for example, if I take a word like every day, it's one word, but it could be split into two different tokens, every and day. So essentially, tokens are not always the same as the number of words, but essentially in general, tokens are the basic units in which you feed text to a language model, and parameters are the internal representation of the trained weights. Now let's take a look at what it takes for large language models to actually function the way they do. So if we take a look at the left side, these large language models are trained on a humongous amount of data. So for example, you could be getting data from Wikipedia, you could be getting data from books, you could be crawling through the internet to extract the data. You could have descriptions of images in the form of text. You could have code data. It could be a vast variety of such data. It is fed to a foundational model and trained. And at the end of the training process, the foundational model understands the context of a language. It may or may not have the domain specific expertise that you need, but essentially a foundational model will understand language. And that is how it is able to predict when you are feeding the model with a prompt, it is able to predict what comes next. So therefore, the output, as you can see based on the applications on the right, it could be question and answering session, it could be text or code generation, it could be writing an article or summarization of different articles, language translation, things like that. right? So the key takeaway here would be that the foundational model is trained still on a large amount of data, and it has the context of a language, and if trained using the right type of data, also the specific context of the domain. That said, with this brief introduction at this point, I will hand off the presentation to Vaghesh, and he will walk through some of the architectural aspects as well as some of the challenges at the edge and how to overcome those challenges. Vaghesh, off to you.
Thank you. Thank you very much, Meghana. So moving forward, I want to talk about more on the technical aspects about how to develop the generative AI application. So one of the core concept of generative AI, which is the architecture of the model. There are multiple architecture that can be used for the model, such as GAN, that's a generative adversarial network, VAE, or transformers. However, transformer is one of the most groundbreaking model that is not only used for text generation, but numerous other AI solutions also for vision generation, image generation, and many sentiment analysis also. Transformers are type of a model introduced in 2017 in a paper titled Attention is All You Need by some of the Google researchers. This model set a new standard for a variety of complex tasks, particularly in regards to natural language processing. The core innovation of Transformer is the self-attention mechanism, and that allows the model to weigh the importance of different parts of input data. For example, different words in a sentence and then process them simultaneously is a part of the self-attention mechanism. This is a significant shift from the previous models that processes data sequentially, one element at a time. These models and the transformer architecture is backbone of all the most advanced AI system. Example, OpenAI's GPT or Google's BERT. A transformer model consists of two different parts, encoder and a decoder. The encoder processes the input sequence while the decoder generates the output sequence. Both encoder and decoder are composed of multiple different layers, and each contains that multi-head self-attention mechanism followed by neural network, feed-forward neural network. This transformer architecture can be used in a different mechanism and can have different models supporting those transformer architecture. One of the architecture is encoder-decoder architecture, where it is primarily used for sequence tasks, where model takes an input sequence and generate an output sequence of potentially different length. The example of usage can be a machine translation, text summarization, or chatbot responses. In this encoder-decoder transformer, we have like encoder to process the input sequence and encodes that in a fixed size vector, context vector, and those fixed size context vector are fed into the decoder part, and then decoder will generate the output output sequence token by token. There is another architecture called decoder-only architecture, and that is mainly used for autoregressive tasks where the output sequence depends only on the previously generated tokens and not on any input sequence. These models are often used for tasks like text generation, large language modeling kind of applications. This decoder-only transformer consists of a decoder. It generates the sequence auto-regressively, starting from an initial token and predicting the subsequent token based on the previous one. Encoder-only is another architecture which is mainly used for the sequence classification or feature extraction. In this, the task involves only processing input sequence and does not require any output sequence. An encoder-only transformer consists of only the encoder part. It processes the input sequence and produces the context-aware representation for each token in that sequence. So this is more about the transformer architecture and how it is used for the LLM side. Can we go to the next slide? Yes. Now, I want to introduce a really new concept of prompt engineering, which came with the generative AI. The concept of prompt engineering might sound different, but it has a great impact on how we interact with AI, especially in edge application where customization is the key. Prompt engineering is a must requirement. Imagine that you are in a unique role where you act as a retail store manager, and your task is to recommend product and services to your customer. Now, when the customer requests, I need, for example, a customer asks that I need help finding a new ice cream flavor. It is a straightforward request, but how can we ensure that the AI response is tailored precisely to what customer needs? That is where the prompt engineering comes into the play. It allows to customize the prompts we give to AI system. These prompts are like the question we ask AI, guiding the responses. The key here is the level of fine-grained control it offers. Customizing prompts give us the ability to steer AI in a direction we want, ensuring that it provides a response that aligns with our specific objective. Moreover, the customization is not just only about precision, it also controls the AI behavior. AI behaves appropriately and follow all our guideline is a requirement. And with the prompt engineering, we can enable that feature. In certain scenario where ethical considerations are important, this level of control is absolutely necessary. Prompt engineering also has a feature of extracting the insight from what the user need, whether it's information or a recommendation or some data which tailored according to the requirement. This is very crucial in making these informed decisions and obtaining any relevant recommendation. Going back to the scenario of retail store manager, the initial customer request I need help with finding the new ice cream flavor is very generic. But with the prompt engineering, when we ask AI to behave as a retail store manager, it tailored the prompt to be very more specific, and it provides a response which asks about the preference of the user. The AI response is very much aligned with a tailored prompt, ensuring that customer receives the exact recommendation they were hoping for. And then this level of precision and control enhances the overall customer experience. This prompt engineering is a really powerful tool in customizing these AI interactions, especially in the edge application where the ability of fine-tuning AI responses is very important. It empowers us to control the AI behavior and extract the desired insight and tailor prompt for the precision response. Going on the next slide, I want to talk about how we can customize the GenAI models. With a new GenAI application, there will be cases where the application will have their own data, and we need to customize the model in a way that it solves the particular challenge. Training the model again from scratch or retraining a model for a larger data set will cost millions of dollars. So there are two important aspects of customization over here, which I'm going to talk about. The first one is the fine-tuned modeling, and another one is the RAG method, which is retrieval augmented generation. First, to understand this fine-tuned modeling, imagine that you have a generative AI model. This model is very well trained it's similar to like a well-trained athlete, which is prepared to run a race. But now we want this athlete to excel in a marathon. Okay, so fine-tuning is similar to specialized training for this marathon. It involves taking a pre-trained model and making it undergo additional training on a smaller or more specific data set for the use case. This process customizes the model, enhancing its performance for particular tasks or domains. In this scenario, you select the best LLM model, retrain or tweak using your own data set, and then use the newly developed model for your application inference task. The advanced type of fine-tuning includes the method called LoRa, that's a low-ranking adaptation. There is another method called QLoRa, which is quantized low-ranking adaptation. There is another method called PEFT, which is parameter efficient fine-tuning. There are multiple other methods available, but each method of fine-tuning are different, and we need to ensure that it fits to the right use case, and then you can use that method to train a new data set with limited computation. Fine-tuning is not the only way to customize the response what you are getting from LLM. There is a new architecture called retrieval augmented generation. There is a technique used in AI, especially in language models. It is having a having a super smart assistant that before answering your question, it quickly looks up the relevant information in the database, and then it will provide you the response. For example, so when you ask a question or give a task to AI, the RAG system first search through the large database that helps to find and retrieve relevant information from the database. It is like doing a quick research to gather the facts and all the details and information from that database. This retrieval can be done using local vector database, hosted or maybe any hosted indexing service like from the major cloud provider, or if you can have your local documents in a PDF text or the Word document format. So you can retrieve that information from that database, and then find that after finding that information, then you provide that crafted question with the question plus relevant information to the base LLM model. It is similar to writing an essay or an answer using the notes from your research. The response what we will get is will have like more understanding about your relevant information, and then the response will be more accurate and detailed. It is useful for complex questions where the AI might not have all the answers available as a part of the base LLM. In summary, RAG helps AI to give better and more informed response by combining with their own understanding with quick on-the-spot research. This solution is easy to implement with open source tools without intensive compute requirement, and can easily work on the edge devices. Going forward, I'll talk more about why GenAI at the edge and not on the cloud. We know that all the usage of generative AI at the cloud and how we are using the ChatGPT and many other AI models. However, there are many use cases and scenarios where we need the generative AI at the edge. It can be your laptop, it can be your edge or client device, or it can be even your smartphone. Generative AI at the edge significantly enhances that response time. For instance, in real-time code generation example, a developer is working on application which require a very quick feedback. With local processing, the time taken to generate and validate the code snippet is drastically reduced. And that enables that faster development cycle and as well as rapid prototyping. This approach also translates to substantial cost saving, which considering that the industrial automation setting, you don't want to send all those data in the cloud and then get the response back. If you have that local processing available in the industrial setting, it will effectively reduce a large amount of cost from the transmission and the storage side of it. Optimizing hardware resources is also an important edge AI application. A very simple example can be a medical diagnosis in healthcare. For instance, local processing of that medical images on specialized hardware can expedite the diagnosis process. This not only simplifies the load on central server, but also ensures timely and accurate medical assessment and improves the patient care. Low-code generation and text generation improve security and privacy. Imagine a scenario where an AI-powered personal journey is created on your device. By generating and storing these general entries locally, this sensitive personal information remains under your control. that minimizes the risk of data breaches or any leaks to the external world. Generative AI at the edge also guarantees that functionality even without an internet connection. A simple example can be in the agriculture field, where edge AI can provide that critical functions like real-time crop health analysis using the image generation and analysis kind of application. And this invaluable feedback can help to ensure that timely decision making and crop management available in a remote farming area also. This approach also stimulates the operation and conserves energy. Like a very simple example can be a smart city where local AI can manage the energy consumption is efficiently. There may be like for retail experience, you can hyper personalize your experience. You can tailor the experience to an individual user. Local AI can analyze the shopper behavior in real time. That generates the personalized product recommendation for that individual, and then it can offer that in-store offers. This creates a very highly customized shopping experience that enhance that customer satisfaction, and it can increase the smell eventually. By reducing that reliance on the centralized data center, generative AI at the edge contributes to the lower carbon footprint also. This eco-friendly approach reflects the commitment to sustainable and environmentally responsible AI technologies. Yep. Now, as we move, the edge computing demands that AI models operate efficiently in a constrained environment. At the edge, we do not have very high-end compute and memory-intensive devices. We have a very limited hardware for the computing purpose. That means that we need to have that model which are lightweight but effective and ensuring that speed and accuracy without overburdening the device itself. The first step in optimization is quantization and compression. That is heavily used in all the edge device applications where you want to deploy the generative AI models. What it means is like there are multiple different mechanisms to achieve that function. One of the largely used mechanism is like converting that FP32 model to a smaller FP16, INT8 or INT4 kind of model. So traditionally, all the models are trained for FP32, and that's a 32-bit floating point precision, and that can be reduced to any of the larger model like FP16, INT8 or INT4, and it also does not reduces the accuracy. Reducing that quantizing and compressing the model is not reducing the model itself, it reduces the size, but the loss in the accuracy is very minimal. Considering a real world application like in a smartphone, if you want to have that facial recognition system, using this lower precision model ensures that a quick and accurate processing without draining the device resources. There are many other techniques available for quantization and compression. One is weight pruning that involves like non-essential weight will be pruned to reduce the size and complexity of the model. There is a activation quantization. It is very similar to weight quantization, but it reduces the size of activations. And activations are like the output of each layer in the neural network. There is another method called Huffman encoding, and that is a new method of compressing the model size. In the industry, there are many tools available for the optimization of any model. One of them tool is like TensorFlow Lite. That is very ideal for mobile and embedded devices, and that allows for easy conversion of full-size model to more efficient version. There is another called PyTorch Mobile that brings that power of PyTorch framework to the mobile platform. There is a ONNX runtime. There is a OpenVINO toolkit, which is a toolkit designed to accelerate the AI inferencing across Intel hardware. There is a Core ML, which is specifically developed for Apple devices and provides that machine learning model integration with iOS applications. There is a TensorRT, which is a high performance deep learning inference optimizer and runtime that is for NVIDIA GPU. There is an open source library called GGML. That's a tensor library for machine learning that enables that large model and high performance on a commodity hardware. So optimizing generative AI models involves not just the technicalities of model compression, but also the selection of right tools for deployment. This optimization is very critical in bringing this powerful AI application on the devices at the edge. It can be smartphone or the edge devices. Yes. Now moving forward, I will outline the flow. Like this is a very standard flow for implementing any generative AI at the edge. To effectively implement a generative AI, it's a crucial to start with the right foundation, and that's the hardware selection. Edge devices must be equipped with sufficient processing capability to handle the demands of AI workload. That includes like selecting devices with the right balance of computational power, memory, and energy to ensure that AI algorithm runs perfectly fine on that hardware. The second part is model and data selection. All the AI models are not suitable for edge deployment. The key is to choose the model that maintains a balance between complexity and performance. The model should be lightweight yet capable to perform the necessary tasks. And the data used for fine tuning or for the RAG method should represent the condition of the model which encounters in the edge environment. Once you have the right model, optimizing it for edge devices is very essential. And that can involve like model quantization, compression, and tuning method to reduce that size and computational demand. Security is also an important concern when deploying AI at the edge. Implementing a robust security protocols ensures that both the AI model and the data which processes at the edge are protected from unauthorized access and other cyber threats. After deployment, that we need to continuously monitor the model deployment and the application performance, and that is a very important piece to ensure that the model is performant on the edge device as well as it provides the right security. This also includes that monitoring of model's performance to ensure that it is operating as expected and updating it to response of the new threats or changes in the environment, and regularly updating the application and model with the new security patches. Moving forward, I want to talk about the risk and ethical dilemma around the generative AI solution. Models can be used for malicious purposes, such as creating deepfakes or automating the spread of misinformation. AI system can accidentally extend the bias if they are trained on unrepresentative or prejudiced data. This can lead to a discrimination in critical areas like recruitment, law enforcement, or loan or legal or loan approvals. With the edge devices often collecting personal data, there is a risk of privacy breaches. This could occur whenever there is a direct cyber attack or unintentional data leaks. Generative AI can replicate and produce work that may violate on intellectual property rights, raising a question about the ownership and originality of AI-generated content. To avoid all this risk for the ethical dilemma, we have like a general guideline which and best practices to consider to ensure that we are meeting the ethical principles while designing the application. The one of the important and main is like to have that ethical framework, and that can be a wonderful practice to have for any application development. The framework can guide the responsible development and deployment of AI technology, ensuring that we serve the common good and not harm the society. To combat the bias, it is very important to use training data that is diverse and inclusive. This ensures that AI models can fairly and accurately serve all segments of the population. Another one can be conducting a regular audit, maybe monthly, quarterly, or yearly, of the AI system that can help detect and mitigate the issue with bias, performance, and ethical standards. These audits can, it's better if it's performed by third party whenever possible. Engaging with the stakeholders, including the public, policymaker, and expert in ethics and law, can also provide a valuable insight into the societal impact of AI and help shape the guideline that reflect the broad range of perspectives. Moving forward, I just want to touch base on the limitations and risks for deploying that generative AI at the edge. Generative AI model require a really large data set of high quality to produce accurate and reliable output. If the data is scarce or poor quality, the model's performance can be severely affected. AI model used for diagnostic imaging in healthcare must be trained on a diverse and high resolution dataset to identify that medical conditions accurately. Inadequate data can lead to a misdiagnosis or poor patient conditions. Generative AI models are often computationally demanding, which can be a limitation at the edge. Uh, Another can be like models may generate the bias or entirely fabricated data known as hallucinations. So in law enforcement, predictive policing tools must be free of bias to avoid that unjust targeting certain demographics, and hallucination in data could reinforce stereotypes and lead to discriminatory practices. Ensuring that AI models are robust and reliable is very critical, especially in a safety critical applications. Generative AI can also produce content that infringes on existing copyright or create any legal challenges. Edge devices many times process very sensitive data, which can be compromised if adequate security measures are not in place. AI system can also influence the social and cultural norm, potentially leading to a negative impact. The decision made by AI system can also raise ethical and moral questions, particularly when those decisions impact human lives. There is always a risk of AI being used in a very harmful purpose. A simple example can be a deepfake technology can create a very convincing fake videos or audios which can defame the public figure or spread false information. Addressing this issue requires a different approach, including the rigorous testing, validation, and ethical guidelines, and also the stakeholder engagement and continuous monitoring. It is very essential to anticipate this challenge and proactively establish a practice to ensure that the generative AI at the edge is developed and used responsibly. So this is the last slide, and now if you have any questions, we can take them.
So there are no questions on the YouTube window. Yeah, I don't see any questions. But yeah, thanks for your insightful presentation. I'll probably ask a few questions if you don't mind.
Absolutely.
Yeah. So I'm really curious about this LLMs on edge. How can you fit an LLM model on edge device? You mentioned some techniques like, for instance, Huffman encoding, and so those will not result in a huge reduction in the model size, right?
No, yeah. So I will provide you our experiment at Intel. So we have seen that any LLM model like less than 10 million, even 13 billion also fits in a very commodity hardware like Intel NUC devices or i7 or i9 type of processor. Most of the LLMs are made to run on a GPU. But with OpenVINO toolkit, you can optimize those LLM and make it run on Intel GPU or even on the CPU also. So there are certain ways where you can run this LLM, smaller LLM models on a specific hardware. If you go for a bigger, larger LLM models like 30 million parameters, 70 billion parameters, you need a data center or NVIDIA's GPU to run them. But for smaller model, for the certain use case, you can easily run it on any CPU. The way it works is like, as you mentioned, the Huffman coding and other approach. But a very simple example is like using any of the toolkit. Like I mentioned a couple of tools, but there are many other tools available in the market. Like a very simple example, OpenVINO is one. There is a GGML where you convert the model into from FP30 to INT4 or even INT2 without compromising on your accuracy. And once you have a very smaller version of 7 billion parameter of, for example, Llama to 7 billion parameter, you can run it on a CPU and get the response back. That works perfectly fine for specific use cases. You can implement the RAG model, which we have experimented. It's a very simplified approach. You don't need to write any algorithm or do it. There are multiple tools available to quantize and compress it. Use any tool and then run it on the edge device.
But the LLMs are typically in terabytes, right? The model size itself is in terabytes. So do you think?
Yeah, so there are few. The smaller models are not in terabytes. The smaller models are more in gigabytes. So LLM 7 billion will be under 30 GB or so.
Oh, okay.
Yeah. So the bigger model, like 70 billion parameters, they are huge in terabytes, but the smaller are in gigabytes.
Okay, so your experiments use some of those smaller models, not like ChatGPT and stuff like that.
Yes.
Llama. Yeah. Okay.
Yeah.
Okay, and you also talked about retraining with private data set, right?
Correct.
So how is that retraining done? So you have this large model, then
Yeah.
how do you add the knowledge? Actually, if you can show that slide, I think it was slide 11 or 10.
Yes.
Yeah, 11. So, so in case of fine-tuning model, you're saying that you get a fine-tuned LLM based on the private data.
Yes.
So you can train layers of neural networks using private data, but how are you going to incorporate them into the base LLM?
So there are few techniques available like LoRa, QLoRa, which helps you to train with a smaller data set. And let me talk about the LoRa mechanism. Okay, so what LoRa is low ranking adaptation. Okay, think of LoRa as like customizing a very powerful computer for a specific job. Okay, it changes a small part of AI model to make it better suited for certain tasks. For retail, there may be few document or few important tasks we need to retrain the model. So it will only retrain that small part, like translating a language or maybe writing poems without needing to overhaul or change anything on the entire thing. This makes it quicker and cheaper way to adapt these big AI models. Like you can take any Llama to 7 billion parameters used with the LoRa techniques, train it with a specific data set. What you are doing is like you're not changing the whole model, but you are retraining certain parts according to your requirement. So that's one of the mechanism to do it. There is another one which is quantized LoRa, and that is a smaller and smarter version of LoRa, which is like packaging the same power into that smaller space. It is also modifying the AI model in a way that uses less memory but still performs really well. Imagine having a huge library of books, but you are able to shrink that books so that they take up less space without losing any information. And then you use with the LoRa where you are retraining the model in a little smarter way, but not all the component, only the specific area what you want to retrain. There is another method available called PEFT. That's a parameter efficient fine tuning. and that is more kind of teaching the old dog new tricks. Okay, and it's a important one because like what we are doing in that path mechanism is like, instead of retraining the entire AI model, it only tweaks few parts. This is like updating a few chapters of a textbook instead of rewriting the whole books. It is very efficient because it saves time, resources, and while still we can uh, have a model learn the new things effectively. There is another concept called deep speed. That is another method, but that is mostly used for training larger AI models. And it has a set of tools that makes this teaching AI models faster and more efficient. I have not personally used the DeepSpeed side of it. I have not yet looked into it. But what they offer is for a larger model, uh, you can retrain and learn and help them to learn quicker without using a lot of compute power. But there are many other techniques also available. As I mentioned, few of them, but there are many other techniques available. Most of the techniques are open source, available on GitHub, but those are the techniques which most of the company use where they want to change the base LLM model with that training data set.
So yeah, I got those points, but see, the model is like a black box, right? It's a serialized file of some terabytes or gigabytes. So how are we going to train just a few layers? I mean, how
So
are you?
what we do is like we change the weight and biases of each layer. So with the transformer architecture, we have encoder. Okay, so encoder is doing is like taking all the input string and then adding that weight and biases and converting into a fine-tuned context vector. Okay, that's how the encoder works. What we are doing is like with the new data, we are changing the weight and biases of all those data, and only the data will not change for all the whole model, but only the new data what we are providing. And with that changes in the weight and biases, whenever we do the inference, it will have a different approach of providing the output and the response.
So it will change the all the billions of parameters.
Not whole, but it will change on the data what we are providing, only the new data, weight and biases of new data.
So the neural network, there's no distinction between new data and old data, right? If you look at the neural network architecture, we have number of layers and number of neurons in the layers. So how exactly does what you said translate to this architecture, neural network architecture?
I need to look into the neural network architecture, what you are mentioning about. Can you provide like more context to that question, Vishnu?
No, what I meant to say is that this is LLM model is like a huge neural network, right?
Yeah.
So there are some layers and then neurons in those layers.
Correct.
So how does, I mean, what does it mean to change the parameters just for the new data set? So there are weights associated with each neuron, right? Each connection.
Yes.
So how do you distinguish the weight specific to the new knowledge, new data set?
So for that one, there is a library available to do that. I can put it in the chat.
Okay, it is still a black.
But how underneath what it is doing, I might not be the right person to answer it. We have used that library, but going underneath, like next level, how they are doing it, I might need to look for the research paper written by the engineers for the LoRa techniques.
Okay. So the same thing applies to the retrieval augmented generation as well. I mean,
so for RAG, it is simpler approach where you are not retraining any model. So for the RAG approach, what we are doing is like we have the data available. So before sending that question to the LLM, what we are doing is like we are searching in our document for that data. Okay. A very simple example is like I have a new ice cream flavor for white coffee. Okay. I have a product description for white coffee. Now the base LLM doesn't know what is white coffee ice cream flavor. So what I will do is like I will use the RAG mechanism where whenever someone asks, like a customer asks, like what are the ingredients of white coffee ice cream flavor, the first part is like it will look into the private data set, and that can be a document, that can be a vector db or index. It will get all the information of white coffee flavor and then send it to base LLM. And what we are sending is like a question itself, like what are the ingredients of white coffee flavor, as well as we are sending the relevant information, like all the product information, what we collected from our document. Okay, so now the base LLM understand like, okay, these are the ingredient of white coffee. This is what the product is about, and then it will respond to the answer of that user. So that way, what we are providing is like a relevant information as well as question, and everything is in the inference side of it. We are not retraining or doing anything. It's a new architecture which is used for customizing Gen AI model for context awareness.
Okay, so you are basically sending the information from the private data.
Correct.
Form of a prompt, is it?
Yeah, and then changing that prompt through the POM.
So the answer from the smart lookup is basically input to the base LLM as a prompt.
Correct. Yes, as a prompt, and
Okay,
then
so
base LLM will provide that response.
Okay, so it's a much simpler approach.
It's a very simple approach, and that is what we have seen like many company adapting it, because retraining will also, like if you use LoRa, QLoRa, or any PEFT technique, you will need a large amount of compute in GPUs and many other hardware to do that job. But with the RAG approach, you don't need any specific hardware. You can run directly on the required inference hardware. You don't need to retrain, maintain a different version, or maintain a separate model. You can use the same base model for the RAG mechanism. So many companies have started adopting this RAG mechanism if that suffice their requirement to provide the response.
Okay, and for the private data also, you use some kind of a language model, or is it something else?
For private data, like how we are doing the smart lookup.
Yeah.
So for that, there are many services like AWS Canva is one of the service which you can do the smart lookup. It is available in AWS, but for local also you have like different vector DB. Fias is one of the technique or one of the open source library. I would say it's available for creating that vector database for all your documentation. So what you are doing is like creating you might have like 100 document as a private data. So you provide that documents to the vector DB. It will index all those documents with a specific word, similar to how Google is searching it. It is indexing, but it is indexing in a local device. And then when you do the smart lookup, it will look for those indexes, provide that relevant information, and then send it to base LLM.
Okay, so it's basically like a vector-based semantic search.
Exactly. Yeah.
Yeah. So so Fias is commonly used, or there's other methods like LSH and.
There are multiple available as a vector. Even MongoDB, you can use it as a vector database. So there are multiple databases available which you can use for smart lookup or for private data. I have seen like various companies using a different one. I have not seen one dominating in that industry, in that tool right now. But Fias is one thing which we have evaluated. we have also evaluated MongoDB also for the edge devices, because our goal was more on the edge devices, how we can use the Gen AI models. So Fayas is one, MongoDB can be another one, and there are many other tools available.
Yeah, Fias is the one from Facebook, right?
Yes. Yeah,
Facebook AI
Facebook.
semantic search or something.
Yes. Yes.
Yeah. Okay. I think we are on the top of the hour. So yeah, these are really very good insights. I'm pretty sure these are very valuable to the viewers. So thanks again for sharing your knowledge today. Really appreciate, and hopefully we'll be in touch for probably some of the future events as well.
Yep. Thank you, Vishnu, for this opportunity.
Thank you, Vishnu.
Thank you. Thank you, Vaghesh. Thank you, Meghna.
Thank you very much.
Take care.
Bye.
Bye.
Bye.